Today we are going to learn about building efficient cache hierarchies. We will explore how to design multi-level cache hierarchies to optimize data retrieval speed and reduce latency, providing you with practical insights into organizing and implementing cache layers effectively. Welcome to our video on building efficient cache hierarchies. In this introductory segment, we will explore what cache hierarchies are and why they are crucial in modern computing systems. Cache hierarchies refer to a layered architecture that optimizes data retrieval speed and reduces latency. They play a vital role in ensuring efficient processing and data handling, especially in complex systems. Today, we will delve into various aspects of cache hierarchies, including multi-level caching, designing for locality, memory hierarchy, and more. By the end of this video, you will have a comprehensive understanding of how to effectively implement and manage cache layers to enhance system performance.
Cache hierarchies are an integral part of computing systems, designed to improve data access speed by storing frequently accessed data closer to the processor. The concept of cache hierarchy involves multiple levels of storage, each differing in speed, size, and proximity to the CPU. These levels are typically organized as L1, L2, and L3 caches. The primary goal is to minimize latency, ensuring that the processor spends less time waiting for data retrieval. The cache hierarchy acts as a bridge between the fast processing speeds of the CPU and the slower access times of main memory, effectively reducing bottlenecks and improving overall system efficiency. Multi-level caching offers numerous benefits, primarily enhancing data retrieval speed and reducing latency. By employing multiple cache levels, systems can store varying sizes of data closer to the CPU, providing faster access to critical information. This layering allows for efficient resource utilization, where the more expensive, faster caches handle frequently accessed data, while larger, slower caches manage less critical data. The result is an overall improvement in system performance, with reduced bottlenecks and increased throughput. Multi-level caching also contributes to scalability, allowing systems to manage growing data demands without compromising speed or efficiency.
Designing cache hierarchies requires an understanding of data locality, which can be categorized into spatial and temporal locality. Spatial locality refers to the tendency of a processor to access data locations that are physically close to each other within a short time. Temporal locality, on the other hand, involves accessing the same data locations repeatedly over a period. By leveraging these locality principles, system designers can optimize cache performance. Implementing strategies that predict and preload data based on these access patterns can significantly enhance data retrieval speeds and reduce latency. Understanding and applying these concepts are essential for creating efficient cache hierarchies. The memory hierarchy in computing systems is organized into different cache levels, commonly known as L1, L2, and L3. Each level has distinct characteristics and serves a specific purpose. The L1 cache is the smallest and fastest, directly integrated with the CPU to store the most frequently accessed data. The L2 cache is larger but slightly slower, acting as an intermediary between L1 and the main memory. The L3 cache, while being the largest, is the slowest among the three, providing a larger storage buffer for less frequently accessed data. Together, these caches form a cohesive system that optimizes data access and improves overall processing efficiency.
Implementing read-through and write-through caches involves strategies to maintain data consistency and optimize performance. A read-through cache loads data into the cache upon a read miss, ensuring that subsequent reads are faster. Write-through caching, on the other hand, involves writing data to both the cache and the main memory simultaneously. This approach ensures data consistency between the cache and the main memory but may introduce additional latency during write operations. Understanding the trade-offs between these methods is crucial for selecting the appropriate caching strategy based on specific system requirements and performance goals. These techniques are commonly used in scenarios where data integrity and consistency are critical.
Designing an efficient cache hierarchy requires balancing cache size, speed, and cost. Larger caches can store more data, reducing the likelihood of cache misses, but they are also more expensive and may have slower access times. Conversely, smaller caches are faster and cheaper but may lead to higher miss rates. The key is to find an optimal configuration that maximizes performance while minimizing costs. This involves analyzing workload patterns, understanding system requirements, and carefully selecting cache sizes and speeds that align with budget constraints. Striking the right balance ensures an efficient, cost-effective caching solution that meets performance targets. Cache eviction policies determine how data is replaced in a cache when it becomes full. Three common policies are least recently used, LRU, first in first out, FIFO, and least frequently used, LFU. LRU removes the least recently accessed data, assuming that data accessed recently will likely be accessed again soon. FIFO evicts data in the order it was added, regardless of access patterns. LFU removes data accessed the least frequently. Each policy has its strengths and weaknesses, and selecting the right one depends on specific application needs and access patterns. Understanding these policies helps optimize cache performance and efficiency. Cache hierarchies are widely used in various real-world applications to enhance performance and efficiency. In data centers, multi-level caches are implemented to manage large volumes of data, improving access times and reducing latency. In gaming systems, caches are used to store frequently accessed textures and game data, providing seamless and responsive gameplay experiences. Additionally, web browsers use caching to store web pages and resources locally, speeding up page load times for users. These examples highlight the versatility and effectiveness of cache hierarchies in different industries, demonstrating their critical role in optimizing performance and meeting the demands of data-intensive systems. In conclusion, building efficient cache hierarchies is essential for optimizing data retrieval speed and reducing latency in complex systems. Throughout this video, we've explored various aspects of cache design, including multi-level caching, locality principles, memory hierarchy, implementation strategies, and eviction policies. By understanding these concepts and applying them effectively, you can enhance system performance, improve data access times, and manage resources efficiently. We hope you found this video informative and insightful, providing you with the knowledge and skills needed to implement and manage cache hierarchies effectively in real-world scenarios. Thank you for watching.